In the sprawling landscape of modern technology, one company stands as the undisputed architect of the artificial intelligence revolution, NVIDIA. Today, its name is synonymous with the cutting edge of AI, powering everything from advanced scientific research to self-driving cars. But NVIDIA's journey to this pinnacle began not in the sophisticated realm of neural networks, but in the vibrant, fast-paced world of video games. This is the story of how a company dedicated to rendering pixels on a screen transformed itself into the fundamental engine driving humanity's most ambitious technological leap. Our story begins in 1993, when three visionary engineers, including current CEO Jensen Huang, founded NVIDIA in Santa Clara, California. Their initial goal was clear: to create specialized processors that could handle the increasingly complex demands of computer graphics. At the time, personal computers struggled to render sophisticated 3D images, relying on the Central Processing Unit, or CPU, to do most of the heavy lifting. This approach was a bottleneck, limiting both the visual fidelity and the speed of early computer games and graphic applications. They saw an opportunity to offload this burden. To understand NVIDIA's breakthrough, it's essential to grasp the fundamental difference between how CPUs and GPUs operate. A central processing unit, or CPU, is like a versatile, highly intelligent manager. It excels at sequential processing, tackling complex tasks one after another, executing a wide variety of instructions with great depth. However, when it came to the repetitive, mathematically intensive work of rendering graphics, calculating thousands of pixel colors and positions, the CPU became overwhelmed, much like a single manager trying to oversee thousands of identical, simple tasks simultaneously. NVIDIA's answer to this challenge arrived in 1999 with the introduction of the GeForce 256. This wasn't just another graphics chip. NVIDIA boldly christened it the world's first graphics processing unit, or GPU. Unlike the CPU, the GPU was designed for parallel processing. Imagine not one, but hundreds or even thousands of smaller, specialized workers, all capable of performing simple calculations simultaneously. This architecture was perfectly suited for graphics rendering, where millions of pixels need to be calculated and displayed in parallel, many times per second. Let's further clarify the distinction. A CPU is optimized for sequential processing, excelling at complex, single-threaded tasks. Think of it as a master chef meticulously preparing one gourmet dish at a time. In contrast, a GPU thrives on parallel processing, handling many simple calculations concurrently. This is like a massive kitchen staff, each member quickly chopping vegetables or stirring a pot, all contributing to many dishes simultaneously. This unique ability of the GPU to process vast amounts of data in parallel would become NVIDIA's most valuable asset, far beyond its initial purpose. With the GeForce line, NVIDIA rapidly became a dominant force in the PC gaming industry. Its GPUs powered increasingly realistic graphics, supporting standards like DirectX and OpenGL, and making immersive 3D worlds possible. Gamers eagerly upgraded their systems, driving demand for more powerful graphics cards. NVIDIA cemented its reputation as a leading innovator, constantly pushing the boundaries of visual fidelity and performance. This gaming success provided a robust foundation, allowing the company to invest heavily in research and development, unknowingly laying the groundwork for its future in an entirely different field. While NVIDIA GPUs were busy rendering dragons and spaceships, a quiet realization began to dawn among researchers: the parallel processing power that made GPUs so effective for graphics could be applied to other computationally intensive tasks. In the early 2000s, some scientists began experimenting with using GPUs for general-purpose computing, repurposing them for complex calculations outside of gaming. This concept, known as general-purpose computing on graphics processing units, or GPGPU, started as an unofficial hack. It hinted at a future where GPUs could solve problems far beyond the gaming screen, but a major barrier remained. The biggest hurdle for GPGPU was programmability. GPUs were designed for graphics, and their programming interfaces were complex and specialized. In 2007, NVIDIA addressed this directly by launching CUDA, the Compute Unified Device Architecture. CUDA was a revolutionary software platform that allowed programmers to use standard programming languages like C, C++, and Fortran to access the GPU's parallel processing capabilities directly. This transformed the GPU from a graphics-specific accelerator into a powerful, general-purpose parallel computing engine, opening the floodgates for innovators in every field. So, what exactly is CUDA? It's more than just a programming language, it's an entire ecosystem. CUDA provides a comprehensive set of tools, libraries, and an application programming interface, or API, that allows developers to harness the immense parallel processing power of NVIDIA GPUs. It effectively creates a bridge between the software and the specialized hardware. Before CUDA, writing programs for GPUs was incredibly challenging. With CUDA, NVIDIA made GPU programming accessible to a much broader audience of engineers and scientists, democratizing high-performance computing and laying essential groundwork for future AI breakthroughs. With CUDA, the scientific community quickly recognized the potential of GPU. Researchers at universities and labs began using NVIDIA GPUs for a wide array of computationally intensive tasks. Everything from molecular dynamics simulations to seismic imaging, and even early climate modeling, benefited immensely from the speed and efficiency of parallel processing. The ability to run complex simulations faster allowed scientists to accelerate discoveries, test hypotheses more thoroughly, and tackle problems that were previously intractable due to sheer computational demands. This era marked the true beginning of the GPU's journey beyond gaming. Then came 2012, a pivotal year that would forever alter NVIDIA's trajectory. A research team led by Alex Krashevsky, Ilya Sutskever, and Geoffrey Hinton at the University of Toronto unveiled AlexNet, a groundbreaking convolutional neural network. AlexNet was trained on 2 NVIDIA GPUs and achieved a stunning victory in the ImageNet Large-Scale Visual Recognition Challenge, drastically outperforming all other competitors. ImageNet is an annual competition where algorithms are tasked with accurately classifying millions of images. AlexNet's success wasn't just a win, it was a clear demonstration of the immense power of deep learning, powered by GPUs, to tackle real-world AI problems. This monumental achievement revealed a crucial truth: deep learning algorithms, which power modern AI, rely heavily on matrix multiplications. These are mathematical operations involving vast arrays of numbers, and they are performed billions of times during the training of a neural network. This is precisely where the GPU's parallel processing architecture shines. CPUs, designed for sequential, complex tasks, would take weeks or even months to train these networks. GPUs, with their thousands of parallel cores, could accomplish the same in days, dramatically accelerating the pace of AI research and development. It was a perfect match of problem and solution. Recognizing this paradigm shift, NVIDIA made a bold strategic move. Jensen Huang and his team understood that the future was not just about gaming graphics, but about powering the burgeoning field of AI. They began to shift their focus and investment from purely gaming-centric hardware to GPU and AI. This wasn't just a minor adjustment, it was a fundamental reorientation of the entire company's mission. NVIDIA started dedicating significant resources to developing specialized hardware and software tools explicitly designed to accelerate artificial intelligence workloads, turning their gaming legacy into a future-proof advantage. As AI workloads became more sophisticated, NVIDIA continued to innovate its hardware. In 2017, with the introduction of its Volta architecture, NVIDIA unveiled Tensor Cores. These are specialized processing units within the GPU, engineered specifically to accelerate the tensor operations that are the bedrock of deep learning. Tensor cores could perform matrix multiplications significantly faster and more efficiently than standard GPU cores, providing an exponential boost to AI training and inference. This innovation solidified NVIDIA's hardware advantage, making their GPUs indispensable for serious AI development. Hardware alone isn't enough, powerful software is equally critical. NVIDIA developed libraries like CUDNN, the CUDA Deep Neural Network Library. CUDNN provides highly optimized primitives for deep learning frameworks such as TensorFlow and PyTorch. Essentially, It's a toolbox of pre-written, super-efficient code snippets that AI developers can use for common operations like convolutions, pooling, and normalization. This saves developers immense time and effort, allowing them to focus on designing new models rather than optimizing low-level GPU code. It made NVIDIA's ecosystem complete: powerful hardware, accessible programming, and optimized libraries. To further simplify the deployment of AI, NVIDIA introduced its DGX systems in 2016. These are integrated AI supercomputers, purpose-built and optimized specifically for deep learning workloads. Each DGX system combines multiple powerful NVIDIA GPUs, high-speed networking, and a full software stack into a single, cohesive unit. This plug-and-play approach removed much of the complexity of building and configuring AI infrastructure, making it easier for enterprises and researchers to deploy and scale their AI initiatives. DGX systems became the gold standard for heavy-duty AI training and development. Today, NVIDIA's impact extends across virtually every domain touched by artificial intelligence. In autonomous vehicles, NVIDIA's Drive platform processes sensor data in real time, enabling cars to perceive their environment and make driving decisions. In healthcare, NVIDIA GPUs accelerate drug discovery, medical imaging analysis, and personalized medicine. Robotics, scientific research, financial modeling, and even content creation all leverage NVIDIA's AI platforms. The transformation from a gaming graphics company to the foundational provider of AI infrastructure is complete, and its technologies are now woven into the fabric of our intelligent future. A significant portion of NVIDIA's revenue and influence now comes from its data center business. Cloud providers, enterprises, and research institutions worldwide deploy NVIDIA GPUs to train and run their massive AI models. These data centers are the hidden engines of the AI era, and NVIDIA's hardware and software are at their core. The demand for increasingly powerful AI infrastructure continues to grow exponentially, ensuring NVIDIA's central role for the foreseeable future. They are not just selling chips, they are selling the very capacity for intelligence. The market has certainly taken notice of NVIDIA's transformation. Once a leading gaming component provider, NVIDIA has soared to become one of the most valuable companies in the world, with a market capitalization exceeding $2 trillion. This valuation reflects not just its current dominance, but the market's confidence in its continued leadership in the AI space. While the numbers fluctuate, the underlying trend is clear. NVIDIA's strategic pivot positioned it perfectly to capitalize on the most significant technological shift of our time, leaving competitors scrambling to catch up. From humble beginnings focused on rendering pixels for video games, NVIDIA's journey to becoming the undisputed king of AI is a testament to visionary leadership, relentless innovation, and a profound understanding of evolving technological landscapes. By recognizing the latent potential in their gaming GPUs for parallel computing, creating the CUDA platform, and then aggressively investing in AI-specific hardware and software, NVIDIA didn't just adapt, it shaped the future. The company that brought us vivid virtual worlds now builds the very foundation of artificial intelligence, proving that sometimes, the most revolutionary transformations come from the most unexpected places.